In this lecture video, we're going to look at some classic, almost a classic problem in physics dealing with Atwood machines, and we're going to look at a technique to solve them quickly and easily. The first thing that we need to do when we're dealing with these kinds of systems is define a common positive direction of motion, because we can see that M1 here is going to be moving, assuming that M3 is more massive than M1. M1 is going to be accelerating up, M3 is going to be accelerating down, M2 is going to be accelerating, therefore, to the right. So we want to define a common positive direction so that the directions of those accelerations are all consistent. So I'm going to say M3 is accelerating down, so my positive direction then is going to be that way. So that makes M3 accelerating downward have a positive acceleration. M1 is going to be accelerating upward, and that's also going to be positive. M2 is going to be accelerating to the right, and that's going to be the positive direction. So that's step number one when you're dealing with these kinds of systems. Step number two always is going to be draw our free body diagram. So over here for M1, we have M1G going down, and we have, let's call this T1, the tension in this rope, going up. M1's accelerating upward because T1 is bigger than M1G. Going to M2, yes, we have M2G going down. We have a normal force going up here. Neither one of those forces is actually affecting the motion of the system here. We don't have friction between the table and M2, so those forces don't really come into play. However, we have a tension in the rope here, and same rope, same tension. As long as there's no mass to that pulley and no mass to the ropes, then same rope, same tension. So I'm going to name this one T1 as well. And then moving to the other side, let's call this T2. And remember that if M2 is going to be accelerating to the right, then T2 needs to be bigger than T1. Continuing this on over to M3, we've got T2, same rope, same tension, going up, and we're going to have an M3G going down. And M3 accelerates down because M3G is bigger than T2. Now, to solve for the acceleration of the system, I am going to consider Newton's second law for the system as a whole. So we've got the net force acting on the system is equal to, this is important, the mass of the entire system times the acceleration. For all of these blocks, the magnitude is going to be the same. And if we're going to consider Newton's second law for the entire system, then we have to be talking about the mass of the entire system. And this is a common mistake made by students. They don't include all of the masses here. So starting on the left-hand side and keeping in mind our common positive direction, let's fill in the forces that are acting on this system. First, we have M1G going in the negative direction, so negative M1G. Then we have T1 going in the positive direction, so plus T1. Moving up to the forces acting on M2, the only ones that are affecting the motion of the system are T1 and T2. T1 now up here is going in the negative direction, minus T1. And you can see now what's going to happen to these T1s. I have a positive T1, I have a negative T1, they're gone. Moving over to T2, this T2 is in the positive direction. Then the other one, acting on M3, is in the negative direction. So again, you can see that that tension is going to cancel out, and then we have plus M3G. Those are all the forces acting on the system that are affecting the motion of the system. We're not including M2G or the normal force. Those cancel each other out. They are not acting in the direction of motion. So here, this is going to be equal to the mass of the whole system. Hey, M1 plus M2 plus M3 times the acceleration. Now, I wrote all of that out, but in actual practice, you can ignore these tensions. T1s cancel out, T2s cancel out, and so the only forces affecting the motion of the system, M3G and M1G. We subtract those and divide by the total mass, you've got the acceleration. So M3G minus M1G divided by the total mass, M1 plus M2 plus M3, is equal to the acceleration for all of those blocks. And in one fell swoop, boom, we've solved for the acceleration. Rather than using another tedious method of 3 equations, 3 unknowns, we could look at Newton's second law for M1, Newton's second law for M2, and Newton's second law for M3. solve for all of those tensions so they cancel out, and then put them all together to find A. But this method right here is far more straightforward. Now, part B on the problem could be to solve for the two tensions, T1 and T2. So if that's the case, then you're going to use Newton's second law for just one of the objects. So to find T1, I could use Newton's second law for just M1. So that's going to be T1, which is going in the positive direction, minus M1G is equal to, now this is just Newton's second law for M1. Let's write that up here. The sum of the forces acting just on M1 is equal to just M1 times its acceleration. So we've got M1 here times A. What's A? A is the thing that we just solved for in the previous. So plug in that lovely expression that we already found for A to this, and you've got an equation now that will give you T1. So T1 is equal to M1A plus M1G. Similarly, we could do the same thing for T2. If we go back, we could solve for T2 using Newton's second law for M2 or Newton's second law for M3. Either way, it's going to give us T2. And you've solved for everything that you've needed to solve for. Differences here, if M2 was not there and it was just M1 and M3, this is more a classic Atwood machine. The only difference is you don't have an M2 down there anymore. It's still M1G on the top and it's still M3G on the top. So classic Atwood machine would be just the pulley there and the two masses like that. And you'd solve it the same method. Make sure you define your common positive direction and use Newton's second law for the system as a whole, with the understanding that the tensions will cancel out. And you can pretty easily see that you're going to get that same equation that we already got down here without the M2. So there you have it. Just be careful, because when we start to talk about pulleys that do have mass, then it's not same rope, same tension anymore. We cannot cancel out the tensions in that case. But that's for another time.